It's a great honor to have a chance to speak here about gauge theory, Yang-Mills theory. I would like to thank the organizer for giving me the chance. So the work in this talk is a joint work with Si Li, who is at Tsinghua University. And also Andrei Lozev, who is in Moscow. Here is a picture I borrowed from a talk by Yang to explain about the relationship of mathematics and physics. So here is a picture. He shows the relationship mathematics and physics. So they interact at the root, the basic concept and basic ideas. At this level, they have a deep interaction. And then he gave several examples of the great scientists to demonstrate this picture. Sorry. I think his idea, his picture are very well demonstrated from the history of science. So as many of the previous speakers have emphasized, the most important concept in Young's work is symmetry. So here we list several important development of symmetries. So first is the Copernicus principle. Actually, he's now called as principle. So he not only didn't consider Earth as the center, even Sun and other place should not be considered as center of the world. And we also have the Galileo relativity, the same laws for all inertial frames. And the Lorentz symmetry was first discovered in Maxwell equations. And Einstein realized it's the symmetry of space-time. That's a special relativity. And also Einstein went on to consider local Lorentz symmetry and diffeomorphism symmetry. So as a result, he found general relativity. And everybody knows that Young's great contribution is to emphasize gauge symmetry. As we know, this symmetry is a foundation of modern physics, in particle physics, and also in condensed matter. So the basic notions of this gauge symmetry, mathematically, so we have a fiber bundle. So the fiber bundle is just a family of vector spaces, that is a vector bundle. You can also consider a family of Lie groups, so that will be a principal bundle. And then for this bundle, if you consider sections, that is a generalization of functions. So for example, all kind of tensors forms are sections. Then you have the basic problem, how to differentiate these sections. So that is a natural generalization of calculus. So this, the generalization, the answer is the covariant derivative. So we use the covariant derivative to differentiate sections. And so A is a section, A is a connection. And the important thing is that covariant derivatives are equivalent up to gauge transformation. So that when we consider the covariant derivatives, we should consider gauge equivalent covariant derivatives. So that is, we should consider gauge equivalence of connections. And so in 4 dimensions, we have this Yang-Mills field and also have matter fields, is fermions and Higgs. And I guess it's also the principle emphasized by Si and Yang along Einstein, that symmetry dictate interactions. So that means if you consider Lagrangian respect to gauge symmetry and also conformal symmetry, and you also consider the scaling properties of renormalizability, then the only Lagrangian you can consider in this setting is the Lagrangian for the standard model. So every terms are used for the standard model. And the last piece of this model has been found. The Higgs bosons has been detected several years ago. So this is a great success of this symmetry principle. On the other hand, mathematically, that's a big challenge. So this is a problem we call a Millennium problem, Yang-Mills and the mass gap. So I guess this was written by Edward Witten, that the quantum Yang-Mills theory is the foundation of elementary particle physics. And its predictions has been tested, but its mathematical foundation is still unclear. The successful use of a Yang-Mills theory to describe the strong interactions depend on a subtle quantum mechanical property called the mass gap. So the quantum particles have positive mass, even though the classical waves travel at the speed of light. So this mass gap has not been established. So even the basic theory of perturbative quantum Yang-Mills theory only established several years ago by mathematicians. So then we should consider, so how to define a quantum field theory mathematically. So basically there are several approaches to define a quantum gauge theory. Basically there are two approaches. One is along the line of Dirac. So his idea is that there's no classical theory. It's completely quantum theory. But he still keeps the concept of classical space-time. And this idea was developed by many mathematicians and physicists. Another approach was proposed by Richard Feynman, that he replaced the minimal action principle, so that is the key for classical physics, by passing equal. But this way, you save the classical concepts, such as space-time, trajectories, and actions. So this is the line I shall explain in my talk. And so here we have a branching point. If you follow the Dirac, we have a number of people following this line. Whiteman, BPZ, and Atiyah, Witten, and Siegel for the topological quantum field theory and conformal field theory in the modern development. So if you follow the line, the path of Feynman, so now, depending on how do you modify the classical geometry, I will explain this in a moment. It branches into three lines, three approaches. So if you consider the space-time keeping the property of both commutative and associative, so that has to be a lattice. So that is like a lattice gauge theory. If you relax the condition of associativity and keep commutativity, and along this idea, we have Zweibach, Costello, and Lee. So this was successfully developed to define quantum Yang-Mills theory in 2007. I will explain this. And then this is the work we want to propose in this talk, that we can also modify the geometry, classical geometry, to be non-commutative. So then we will propose a new approach to regularize quantum Yang-Mills theory. So I guess everybody knows where the Feynman's partial integral are coming from. So basically, it's a property if you want to calculate amplitude from an initial state to a final state, then the probability has to be the sum from an initial state to some immediate state. And then immediate state to final state. You sum up over all the medium state. So that gives you a partial integral. But this partial integral, everyone knows, there are divergences. There are infinities, many infinities. For example, if we consider even a simple operator like gamma phi, since the Hilbert space is infinite dimensional, so the operator is not a trace class. So then the trace is not well defined. So then we have to regularize this trace by exponential small terms to regularize. But if you regularize, there are many problems. If you consider a 3-point function, you have the multiplication, and if you consider a regularization, so then you have a problem. So if you regularize this, you have this propagator you replace by a regularized propagator. Then this 3-point function defined a multiplication will be look like this. But after regularization, the associativity is broken, the property of associativity. So that means if you consider these two diagrams, so that means A, B, and C to D. First A and B and C, then to D. Is not equal to A and B and C to D. So these two are not equal. So that breaks the property of associativity. Somehow, this broken property can be saved if you consider a homotopy property. That is, your theory are still homotopic, are still invariant up to homotopy. So if you consider the property up to homotopy, then you have this associativity. So then you have this lot of lines. But this line, that means a lot of multiplication. This multiplication we now call the A infinity structure. So associativity can be restored. So if you consider associativity, a homotopic property, for example, if you consider conjugacy, that gives a part of homotopy. You can also have other things to produce homotopy. So then, as we saw, you have this. You have A infinity structures. So using this method, the first one to use this method was by Zweibach, that he constructed his closed string field theory. He used a BV formalism to construct this closed string field theory and use this homotopy to successfully find solutions for the quantum master equation. So this is an important approach. So BRST is not convenient. It's better to double the field. So you consider BV quantization. So if you consider BV quantization, there are two steps. So the first step is more or less easy. So you consider the classical master equation. So that is equivalent to the action is preserved by gauge symmetry. So this part is easy. But then if you consider quantization, you have to solve this quantum master equation. There's no anomaly for this quantization. But usually you have obstructions to solve this equation. And then you use the trick of this homotopy in several cases. This case for Yang-Mills theory. This problem was solved by Kevin Costello in 2007 in the 4-dimensional space. If the gauge group is a simple gauge is a simple Lie algebra, then the quantum Yang-Mills theory can be defined. So this is first mathematical definition of a perturbative quantum Yang-Mills theory. His solution is published as a book. It first appeared in the internet, now it's published by AMS to explain his solution to this problem. You know, for the many people working on axiomatic field theory, but they only can construct a scalar field theory mathematically. So only in 2007, so quantum Yang-Mills theory was constructed mathematically. And soon, this method was also applied to a quantum theory of Kodaira-Spencer gravity. So this theory, what people call the topological string theory of B type. Then the basic fields are the complex structures of a Kähler manifold. So then you consider this Kodaira-Spencer action, and the critical points are the integrable complex structures. So this was appeared in string theory. And this theory was defined using the method of Costello by Slee, so one of our collaborators, in several years ago. Because previously, people can only consider topological string theory of genus 0. Now he can define this theory for all genus. So this is really a quantum theory for quantum for topological strings. And so now we consider the another variant of space-time. So you can consider using algebra to describe a space. So everybody knows there's a theorem of Geifeld. So for any space, topological space, you consider the C-star algebra of continuous functions of the space. And then these two spaces are topological equivalent if only if this C-star algebra are isomorphic. So that means this topological property of the space are encoded in this space of functions. And so you can use a space of function to describe this space. And then you can use ideas in this algebra to describe figures. Yes? Yes, we can. No, here is a space. It's just space of functions. Well, you can consider sections as a shape. Yeah. So here you consider just a continuous function for ordinary space. Yes. So then, from this algebra, how to construct points and figures, you need to consider ideas. So if you consider maximal ideas, that gives you points. If you consider other ideas, that gives you figures. So this way you can describe the space by algebra. So that gives us three possibilities. So if you keep, so now we want to modify the space by consider the function of space. So if you keep the property to be both associative and commutative, and you also want to be finite, then you consider the lattice gauge theory. So you only consider finite points. So that is the approach of lattice gauge theory. And if you want to break associativity, so then you need to bring homotopy to cure associativity. So then you have this infinity structure. So that was approached by Zweiberg and Costello. So now today we propose a third approach, that we can relax this condition of commutativity. So then you can consider non-commutative variation of the space-time. So in this case, the space of functions can be replaced by finite dimensional matrix model. So it still be finite, so that you can define the theory. And then, so the theories are well defined for each approximation. So then you probably can use this to regularize the theory. So the continuous space as a limit of a non-commutative space. So that is the approach we want to emphasize today. So to do this, we need to emphasize that we not only consider space, but also we consider the differential forms over the space. So that is, we should consider superspace. So the space with bosonic coordinates and also fermionic coordinates. So this is called a superspace. So if we consider superspace, then you consider functions over the superspace. So that gives the differential forms on the bosonic space. Because we will see, as long as we have these differential forms, it's not difficult to define a Chern-Simons theory and a Yang-Mills theory. So we will give the definition. So that depends on construction of forms over space. So here I'll give you an example. That's a well-known example of a fuzzy sphere. So for a fuzzy sphere, for two variables, complex variables, you consider a space of polynomials. It's like a space of C2. And then you consider all kinds of operators acting on these polynomials. So you consider a special operator like this. This is a Pauli matrix. And for this operator, it's easy to see that this operator acting on the polynomials of same degree is an invariant subspace. So that you have an invariant subspace for these operators. And then if you restrict these operators on this invariant subspace, it's easy to see that the square of this operators is equal to 1 plus 1 over k. So this gives a fuzzy sphere. Actually, so these operators generate a non-commutative space. It is a finite dimensional space. So if you have a space and also forms over the space, so that means you have a differential graded algebra and you have an exterior derivative. And you also have a product because it's algebra, you have a product. You can multiply forms. So then we can define a lot of gauge theory. For example, here, we can define this called a BF theory. So, okay. So here you have this exterior derivative and multiplication. So dual, you have the dual. So that gives you a BF theory. That's a two-dimensional theory. I think first proposed by Witten. You can also define Chern-Simons theory if you have an invariant non-degenerate pairing. So this is a definition of Chern-Simons theory. I think this action was also proposed by Witten and also by David Gross, and over a special non-commutative space given by Lie algebra cohomology, and also proposed by some other people to use this to study fractional quantum Hall effect. So this is a picture. So you see the states. So you restrict it to a cutoff. So for the state, you have a cutoff of energy. And then this is a vacuum energy. You consider this vacuum expectation. As you have further and further cutoff, you have the edge state. You have a drop, like a droplet. So that is you back to the operators to functions. And also we can define this action for Yang-Mills. So that was what we proposed today. So for Yang-Mills, the definition is not so straightforward because we have to have a metric. So to deal with the metric, it's better to express this metric as a product of one forms. We use this one form to define Yang-Mills action. Actually, you can also use these event forms to define action for gravity. This was proposed by Palatini. And here is the action for Yang-Mills. As long as you have differential forms, and we also have auxiliary product, using this differential form and the auxiliary product, that's for the background, we can define this Yang-Mills action for non-commutative Yang-Mills. Actually, we construct a lot, as we before, we construct a lot of non-commutative space, which are finite dimensional, depend on n, the cutoff n, as the energy of state. So we can use this action. So this action is well defined because it's finite dimensional. It's simply a matrix model. You can just using trees for the Yang-Mills theory. So what we propose is to use this action to construct a usual ordinary Yang-Mills theory for the continuum. So that is a commutative space. That's infinite dimensional. So we propose to use a non-commutative space as approximation to a gauge theory of a non-commutative space. Actually, this phenomena appears, as we saw before, naturally in fractional quantum Hall effect. That is in Chern-Simons theory. I believe this morning, also as discussed by Professor Ma, for this Thomas Feynman model, that's in the same spirit of a one-dimensional quantum system. If you consider large n, you consider some n, so that's a cutoff. It's just like a matrix model. So then if you consider this is actually really a large n limit as a Yang-Mills theory. I think this might be a very natural proposal to regularize quantum Yang-Mills theory. Thank you.
Thank you. Very good. Other questions?
Yeah. Mm-hmm.
As you know in mathematics, just now you have shown us this A infinity structure,
yes.
right? If we map spaces into a kind of some space endowed with this A infinity structure, we get cohomology structures on the source space, right? So in this case, just now you have shown us like exotic, like non-commutative sheaves of functions, like for instance, you use the space in some sub-algebra of some C infinity algebra, and so on. So in this case, is it true to understand just now this space endowed with non-commutative sheaves of functions as the target of the sigma model?
Actually, yeah. So the idea is quite simple.
Yeah.
It's kind of a cutoff of the state up to some energy scale. So this way you have a very natural matrix model.
Yeah.
So then you consider to raise your energy higher and higher. So that is like a large n limit. So that will give you the theory very naturally.
But
yeah.
If you restrict the cutoff, then in this case, because we are considering a sheaf of matrices, right, and
yeah.
on some open set, then if we put such thing, then the homotopy type of this space I can describe that already changes.
So this way, if you have the cutoff,
yeah.
then the space-time becomes non-commutative. But if you let the energy go to infinity, so then you restore this commutativity of space-time. Yes. So that's very easy to see. Yeah.
So the one. I'm sorry. Yeah. So
yes. Yes. Mm-hmm. Yeah, maybe you can. Yes, later. Yes, yes.
We'll take that later again.
Okay, thank you.